Welcome to the laboratory session number 2. Today we are going to see an experiment that is used to determine the band gap of a semiconducting material using a post office box. This is the post office box, and here we do have several resistances. This represents P, this represents Q, and all these 4 dials constitute resistance R. Again, this post office box also works on the principle of Wheatstone bridge. So as we had seen earlier, we have 4 resistances in a Wheatstone bridge. P and Q are known equal resistances. This S is a variable known resistance, and this R is the unknown resistance. And here the semiconducting material we are going to use is silicon, and the device you call it as thermistor. Thermistor is nothing but it is thermal resistor. You know, for a thermal resistor, the resistance is not constant, but it depends on its temperature. So you already know the property of a semiconducting material. A semiconducting material is made up of covalent bonds, which is a weak bond. When you raise the temperature of a semiconducting material, the covalent bond breaks, releasing free electrons into the lattice. And when the number of free electron increases, the electrical conductivity of the semiconductor increases, and consequently the resistance and resistivity of the material decreases. That is, when you increase the temperature of a semiconducting material, the electrical conductivity of semiconductor increases, leading to the decrease in the resistivity or resistance of the semiconducting material, and hence we say the temperature coefficient of resistance of a semiconducting material is negative. That is, there is an opposite trend here. When you increase the temperature, the resistance decreases, and hence you say the temperature coefficient of resistance is negative for a semiconducting material. Here the semiconducting material we are using is silicon, that is in the form of a device which is called thermistor. This device you call it as thermistor, and the thermistor stands for thermal resistor, which means that its resistance is not constant, but it can be varied with respect to temperature. If you change the temperature of this resistor, the resistance of this material changes, and by finding the variation of resistance with respect to temperature, and by drawing a graph between the temperature and resistance of this semiconducting material, we are going to find the band gap. As you all know, band gap is nothing but it is the energy difference between the top of the valence band and bottom of the conduction band. So for this experiment, the basic working principle is this Wheatstone bridge. So this P and Q constitutes known equal resistances. R is a variable known resistance, and S is the variable resistance, and R is the unknown resistance. Here the unknown resistance is nothing but this thermistor device, this semiconducting material. So we are going to decrease the temperature of the semiconducting material, and we are going to find the resistances at different temperatures. So here, as I already told you, in this post office box, this represents P, this represents Q, and these all 4 dials corresponds to the variable resistance S, and this unknown resistance R is nothing but the semiconducting device. And here we have this post office box. The connections in post office box is very simple. In the 2 terminals, between these 2 terminals, we need to connect the eliminator, right? So here, a 2-volt eliminator. Here it is written as B. This B represents battery. So from these 2 terminals, you need to take 2 wires and connect them to the battery. And here we have an X. It is written as X here. So in between these 2 terminals, you need to connect the unknown resistance. So this is our unknown resistance. So these 2 terminals were connected to this unknown resistance. And here we have 2 more terminals, which is written as G. G represents galvanometer, right? So this is these 2 terminals are given to a galvanometer. Now you need to keep all the dials to 0, right? You need to keep this P and Q at equal values. I have kept P and Q to be equal to 1000. We can keep it as 10, we can keep it as 100, we can keep it as 1000. But you need to remember that the resistance in P should be equal to resistance in Q. So P should be equal to Q, and here P is equal to Q is equal to 1000 ohms, right? Let me note it down in the table. So in the temperature, we need to measure the temperature using a thermometer. This is an alcohol thermometer. As it is summer season, usually the room temperature comes around 27 degrees Celsius. But since it is summer, as you can see here, the temperature is around 33 degrees Celsius. Right? So let us note the temperature as 33 degree Celsius, and here the temperature is written in degree Celsius. In the next column you need to convert it to Kelvin. So to convert it to Kelvin, you need to add this 33 with 273. Let us add 33 with 273. So the result is 306, which can be written over here. So it is 306. In the P we have 1000 ohms. In Q also we have 1000 ohms. This is the variable resistance. Yes, we need to vary all these 4 dials to make this galvanometer to show zero deflection. Actually, the bridge will get balanced when the resistance is P plus S, when it equals Q plus R. This R is unknown resistance. P is already equated to Q. So when you make this variable resistance S to be equal to this unknown resistance, your galvanometer will show you null deflection. In other words, when your galvanometer shows null deflection, it means that the resistance that is kept in the variable resistors S will be equal to this unknown resistance R. Right? So now, out of these 4 dials, we need to use this 1000 dial first. Right? You can check here. This is into 1000. This dial is into 100. This dial is calibrated into 10, and this dial is calibrated into 1. Now, you need to, there are 2 switches given here. You need to press them to check the deflection in the galvanometer. Now, the things are at room temperature. I mean, the thermistor is at room temperature. We had given the temperature in Kelvin also. We had taken up the resistances in P and Q as 1000, and we need to adjust this value of S, that is the resistances in these 4 dials, to make the deflection in the galvanometer to be 0. Let us do the experiment. First we need to click on this dial. Before that, let us switch on the battery. So after switching on the battery, make sure that all these 4 dials are in 0, right? Are at 0 position. See here, it is 0. In 10 dial also it is at 0. In 100 dial also it is at 0. And in 1000 dial also it is at 0. Now you need to do this resistances in the order of 1000, 100, 10 and 1. Now keep all the resistance, all the dials at 0, and click both the switches simultaneously. See here what happens. See, when you click the switches, you have to click the switch momentarily. You should not press it down for long. You press it momentarily and check where is the deflection in the galvanometer. See, for all these 0 dials, this 1000 is it in 0. When you momentarily click this, you will be having a deflection in the galvanometer, right? You need not, there is no need to press the switch for long. You have to do a momentary kick, right? So now for 0 in the 1000 dial, you have got the deflection to the left extreme, right? Now what you can do is, you can make this dial to read 1, right? Now the resistances, now the resistance in the variable resistance R is equal to 1000. Now give a momentary press to the keys and check where is the deflection. See, it is slightly moving towards the left, right? So what we can do again is, as long as this deflection is towards one side, you have to increment the dial, right? Now let us keep it at 2000 and give a momentary kick. Check the deflection galvanometer, it is to the right. Now there is a change in direction. For 0 in the 1000 dial, the deflection is towards left. For 1000 in the 1000 dial, again the deflection in the galvanometer is towards left. And when you move this dial to 2000, this galvanometer shows you a deflection in the right side, right? So there is a change in direction from left to right when you raise the resistance from 1000 to 2000. So whenever there is a change in the direction of deflection, then you need to keep this dial in the previous position, right? See, so now I need to keep the dial in the 1000. See, for 1000 it is to the left. See here, it is deflecting very little towards the left. And for 2000, let me change the dial. For 2000, the thing is deflecting towards the right. So I have to keep the 1000 dial in 1. Right? Now the resistance, what we had found out is the resistance of this unknown resistor at room temperature is lying between 1000 and 2000. Right? Now we are going to narrow down the value of resistance. So now we need to check this 100 dial. For 0 in the 100 dial, the deflection in the galvanometer is towards left. Right? It is very slight towards left. Now let us increase the dial, increment the resistance in the dial 100. So let me put it to 100. Now give a momentary kick. You can see it is deflecting towards right. So for 0 it is towards left, and for 1 it is towards right. So what I need to do, I have to keep the 100 dial at 0. Right? Now we need to, what this represents is, here the resistance is 1000, here the resistance is 0. Right? I mean the resistance, the total resistance is, the resistance of this resistor lies between 1000 and 2000. Right? Here it is lying between 1000 and 2000. Here it is lying between 0 and 100. So the total resistance is equal to, the total resistance of that the resistor lies between this and this. That is 1000 and 2000. Right? Let us go with this one. For 0, you can check the deflection in the galvanometer. It is equal to, it is deflecting slightly towards the left. Now let me increment in the 10 dial. Let me put it to 1. Check the deflection. Again it is towards left. So let us go with 2. You can check the deflection here. Again it is to the left. Again it is to the left. So let us put it to 3. Again the deflection is towards left. Slightly towards left. So let us put it to 4. Again it is towards left. It is towards right. Check it out. It is moving towards right. So for 4 in 10 dial, the deflection is towards right. So for 3 it is towards left, and for 4 it is towards right. So we need to keep the dial at 3 itself. Now the total resistance is 1030, and the galvanometer will show null deflection between 1030 to 1040, because the direction changes between 3 and 4. So null deflection will be between 1030 to 1040, or in other words I can say the resistance of the given thermistor should be between 1030 to 1040. Now let us change the dial into 1. That is, let us keep it at 0, and it shows deflection towards left. So let it increment to 1. Again the deflection is slightly towards left. Let us change the dial to 2 and check the galvanometer. Again the deflection is slightly towards left. So let us increment the 1 dial again to 3. Now again the deflection, there is no change in deflection. So it remains at 3. Check it up here. There is no change in the deflection. So we can take this as the exact value, right? So for this value, the galvanometer shows null deflection. That means now the value of resistance in R is equal to the resistance of the thermistor. So we have 1000 in 1000 dial, 0 in 100 dial, 3 in 10 dial, and 3 in 1 dial. So totally the resistance is 1033. So let us take the value of that variable resistance S as 1033, because our galvanometer shows null deflection, which means that the 1033 in the variable resistance S is equal to the value of the resistance of the thermistor at room temperature. So let us take the value of S as 1033, and how will we calculate R? The formula is R is equal to P by Q is equal to R by S, or R is equal to S into P by Q. And we have the value for S. The value for P is 1000. The value for Q is also 1000. So let us strike off this P and Q. So R is equal to S. So since S is equal to 1033, let us take R is also equal to 1033. Now what is the next column? We need to find ln R. How will you calculate ln R? You need to use a calculator. Use the value of R we had found out. We have found R as 1033. Now you take the ln value for 1033, and please remember the resistance R will take the unit of ohm, and the ln R will not take any unit at all, right? It is merely a number. So let us press ln symbol in your calculator and then press the value of R. Here it is equal to 1033. So let us press ln in the calculator, then we'll input the number as 1033, 1033. Press the equal to symbol, you will be getting some value. We need to take 4 digits after the decimal point. So let us take 6.9402. So the value for ln R is 6.9402, and please remember there is no unit for ln R. The next column is we need to find the reciprocal of temperature, that is in Kelvin, right? We have temperature in Celsius as well as in Kelvin, but we need to take the reciprocal of the temperature value that is given in Kelvin, right? So we need to take 1 by value of temperature in Kelvin, that is 1 by 306. So again that is equal to 3.267973 something into 10 power minus 3. That 10 power minus 3 is already written in the column head of the last column. So no need to bother about that 10 power minus 3. Let us take the numerical value alone, that is 3.2679. Since the fifth digit is 7, let us take this 79 as 80. So our value for 1 by T is 3.2680. Let us write it as 3.2680. So we have completed the determination of resistance at room temperature. Similarly, we need to determine the resistance at different temperatures starting at 80 and 78, 76, 74, etc. up to 60. For that, we have to take hot water in a beaker, and in the test tube, we can insert the thermistor along with the thermometer, right? Make sure that your thermistor stays at the bottom of your test tube, and you need to keep the thermometer in a good position, in a convenient position, so as to check the reading. Make sure your thermometer as well as thermistor stays at the bottom of your test tube, and keep the test tube in the beaker which is filled with hot water, right? So let us take hot water around 90 degrees Celsius, and make sure you're keeping the overhead fan switched off. Check the temperature of your thermometer. When the temperature comes to 80 degrees Celsius, you need to find the resistances as before. So you have to keep all the dials to 0. Then when your thermometer shows 80 degrees Celsius, you have to vary all the resistances, and starting from 1000 you need to vary the resistances, and you have to find the resistance which gives null deflection in your galvanometer, right? You need to repeat this procedure for each 2 degree fall of temperature starting from 80 degrees Celsius, 80, 78, 76, 74 up to 60. So you need to take water nearly around 90 degrees Celsius. Make sure you are keeping your thermistor and thermometer in the test tube, in the bottom of the test tube, and keep it in the beaker. Then you need to take the value of resistances. The value of resistances in the S, variable resistance S, that is in all the 4 dials, so that your galvanometer shows null deflection, right? So that is how we need to do the values. And when you increase the temperature, the resistance should decrease. And since here you are decreasing the temperature, the expected value of resistance should increase, right? So make sure the trend is coming like that. That is, when you decrease the temperature, the resistance should increase, right? And you need to draw a graph between 1 by T and ln R. Ln R should be taken along y-axis, and 1 by T should be taken along x-axis. Here is a sample for you. So Here the temperature is varied from 68 up to 50, and they have done the determination of resistance for room temperature first, then they have done it from 68 for 2 degree fall of temperature up to 50 degrees Celsius. You can check here when the temperature decreases, here the resistance is in increasing trend, right? So that is the property of a semiconductor, that is TCR for a semiconductor is negative. So whenever you decrease the temperature, the resistance is going to get increased. You try to calculate ln R as usual. Calculate the value for 1 by T, that is in Kelvin. And see here, it is in Kelvin inverse, and ln R should not have any unit, right? I remind you once again, ln R is simply a number. R will take the unit of ohms, but ln R will not take any unit. It is merely number, right? So you can finish the observation as well as calculation for ln R and 1 by T. And here is a sample graph for you. 1 by T is taken along x-axis starting from 2.92, and ln R is taken along y-axis. And check here, 1 by T is in 10 power minus 3 Kelvin inverse, and ln R is mere number. It is taken along y-axis, and you will be getting points on the graph. You try to put a straight line which connects maximum number of points. Even if there are 1 or 2 or 3 points that is getting outside this straight line, it doesn't matter at all. It might be the variation in temperature, or it might be the delay in noting readings. So there are some experimental errors. So leave those points, but try to put a straight line which connects more number of points, right? And you take slope between 2 points that lies on the straight line. You need to find the value of dy along y-axis, and you need to find the value of dx along x-axis. Try to calculate the value of dy by dx. So 0.15 divided by 0.04 into 10 power minus 3, that is x-axis is in 10 power minus 3 Kelvin inverse. When it goes to the numerator, it will become 10 power 3 Kelvin, and division of 0.15 by 0.04 will give 3750, right? So actually it is 3.75 into the 10 power 3 Kelvin. So it becomes 3750 Kelvin. So this is the value of slope, that is dy by dx. Now what is the formula to calculate band gap? Eg is equal to 2k into dy by dx. It is not in joule, it is not in electron volt, but actually it is in joules, right? Dy by dx is the slope value, and k is the Boltzmann constant. And this value gives band gap in terms of joules. If you want to calculate in electron volt, you need to do some you need to write the scale also. In x-axis 1 centimeter is equal to how much, and in y-axis 1 centimeter is equal to how much, right? Please remember, along y-axis you should not write any unit, and along x-axis it should be some numerical value into 10 power minus 3 Kelvin inverse. It is the calibration on the x-axis. And please check, you are not writing any unit along the scale of y-axis. Now you have calculated dy by dx as 3750 Kelvin. Now let us substitute this value. So we have Eg is equal to 2k into dy by dx. That is in joules actually. But if you want it in electron volt, you have to divide it with 1.602 into 10 power minus 19. So the value of Boltzmann constant is 1.38 into 10 power minus 23 joule per Kelvin. It is not kilogram actually, it is joule per Kelvin. So 2 into 1.38 into 10 power minus 23 into the value of dy by dx, that is 3750. So Boltzmann constant is in joule per Kelvin. It is not joule per kilogram. It is written wrongly. So the value of Boltzmann constant is actually joule per Kelvin. So 2 into 1.38 into 10 power minus 23 into our value of dy by dx in Kelvin. That Kelvin and this Kelvin in the denominator of Boltzmann constant will get cancelled with each other. So what we are getting for Eg is in joules. So the value of Eg we are getting here is in joules. In order to convert it to electron volt, we need to divide that value by 1.6 into 10 power minus 19 coulombs. If you divide the value by 1.6 into 10 power minus 19 coulombs, we can convert the value of joules into electron volts. So Eg is equal to 0.6468 electron volt here, right? So this is how we need to calculate the band gap of a semiconducting material using this post office box. Thank you. I hope you have understood how to do this experiment using this post office box. Thanks again.